So, I love buffers. We're going to learn about buffers today. It's in chapter 18. What is a buffer? Sometimes my wife and I were like, well, we got this big bill coming up. Let's put money here. We need to leave this much in our checking account as a buffer. What's that mean?
Isn't it just I don't know in the chemistry terms, but if it isn't buffers like protection?
Yeah, protection. That's a good idea. We say buffers resist a change in pH. What does that mean? Well, let's find out here. First, let's think about a weak acid. And there it is, Ka for weak acid. I want to write the Ka expression. What's that going to be? It's going to be our products, hydrogen ion. These are all aqueous. We're just going to assume everybody knows that. All right, now, what if I take the log of both sides of this thing? I'm going to come up here and I'm going to go log of Ka equals the log of H times anion over HA. Now it turns out I can think of this thing as a product of log of H times this thing. So what do you know about your log identities? Log of A times B is the same thing as what? All right, so what that means is, I'm going to write this again, log of Ka equals the log of hydrogen ion plus the log of anion. All right, so here's this log identity. A log of a product is the same as the sum of the individual logs. Now I'm going to do some algebra or arithmetic on this. I'm going to minus the log of hydrogen ion from each side. And while I'm at it, I'm going to minus the log of Ka from each side. So what I'm going to end up with is negative log hydrogen ion is equal to negative log Ka plus the log of A minus A. Now we've reached a beautiful part in our lecture because you all can tell me what has the definition negative log of hydrogen ion? pH. And what has the definition negative log of Ka? We remember negative log of anything, we called it P, whatever. Like, so negative log.
It's POH.
Negative log of OH is POH. What must this be?
H3.
Well, we had pKw. This is just going to be P what?
Ka.
pKa. All right, so I've taken my equilibrium expression here for weak acid, applied the property of logs, and logified the equation, my favorite word. And I have this handy-dandy equation right here called the Henderson Hasselbalch equation from the guys who came up with it. So now that we've done that, and you see where it comes from, I'm going to put it up here as a heading. And that's kind of our buffer equation. So what is a buffer? A buffer is anytime you have a weak acid and its conjugate base, it's going to try and have a pH around the pKa of that system. And here's what we say. We say if we have some HA and we have A minus, whenever we add hydroxide, that's going to convert some HA into A minus. And whenever we add some strong acid, we convert the conjugate base into the weak acid. So in order to have a buffer, you must have a weak acid and its conjugate base. A strong acid and its conjugate base is not a buffer. But a weak acid and its conjugate base resists a change in pH. That's because when you add strong acid, you can convert some of the conjugate base into weak acid. Likewise, whenever you add some hydroxide, you're going to convert weak acid into conjugate base. And that's about it. That's how a buffer works. Any questions? All right, well, I've done this long enough. Students really pull their hair out with buffers. So we're going to just go off into the woods somewhere here. Imagine 1 liter of pure artesian spring water. I'm thirsty just thinking about it. Why are we talking about this? Well, water isn't a buffer, but based on what you've learned so far, what is the pH?
7.
Right. All right, so far so good. Now let's do this. To our nice artesian spring well water, we're going to add just 1 ml of HCl. We want to ask the question, what will the pH be? Now, a lot of times I get the deer in the headlight look. Well, whenever I'm stuck, I just look and grab some units. There's the thing with the most units. I'm going to just start there. I don't know what to do. I'm going to start where I see some units. All right. And what does this uppercase M mean?
Moles per liter.
Yeah, moles per liter. So if I write that in, I'm going to go something here like, well, how many liters did I add?
0.1 milliliter.
0.001, right? 1,000th of a liter is a milliliter. All right. Now this could tell me something. Maybe I'll put what it tells me right here. It tells me how many protons or hydronium ions I have added. Now what I'm really going to do here, I'm going to use this V1 times M1 equals V2 times M2. And since this is a strong acid, if I can just find the molarity after I dilute it, I'll know the molarity and I can then solve for pH, right? All right, so I'm going to multiply by something that looks like this. Maybe I'll put a 1 in there. How many liters will I have after I add 1 ml?
1 liter and 1 ml.
Yeah, that many liters. That's not a big change, right? So then I pull out my calculator. 0.1 times 0.001 divided by 1,001. And what is this? Molar hydronium ion, or HCl. But since this is a strong acid, it completely disassociates. So, and this is greater than 1 times 10 to the 6. That's where we have to stop taking the log of molarity to figure out the pH. All right, so we can go pH equals negative log 9.99 times 10 to the 5th. Pull out our calculator, and what do we get? 4. Perfect. This equals 4. So I went from a pH of 7 to a pH of 4. What kind of change in pH is that?
Increase in pH?
It's a decrease.
Decrease.
Just what's the change? How many pH units?
3.
3. And that's kind of huge because this pH thing is a logarithmic scale. All right, so we went from neutral water to bam, acidic water, pH of 4. Oh, I almost got way carried away. So I'm gonna ask another question. What's the solution's pH after adding 2 mils of 10th molar sodium hydroxide solution? So I had a nice pure liter of water. I put 1 mil of 10th molar HCl. pH plummeted down to 4. Now I'm going to add some base. And I'm going to add twice as much. So will I neutralize all the acid that I added?
Should.
I should, right? And yeah, so, you know, maybe I might need a sodium hydroxide, HCl. So 1-to-1 stoichiometry, right? What's another word for stoichiometry? Mole accounting. I just coined that this morning. So I'm going to start out the same way here. I got 0.1 molar sodium hydroxide, and I could just put hydroxide, and then how many liters? 0.002 liters, and I'm just going to realize uppercase M is moles per liter, so I'm going to find moles hydroxide. Pull out your calculator. 0.002 moles of hydroxide. Well, I just added this many moles of hydronium ion up here, or hydrogen ions. That's going to neutralize some of this. So then this means I have 0.0001 mole of hydroxide left over. And if I want to do a conversion here, if I'm after molarity of hydroxide solution, what am I going to put down in the bottom here?
The liters.
Liters. And how many liters do I have at this point? Absolute 1.003 liters. And I pull out my calculator and do that. I'm going to get 0.997 times 10 to the -5th molar. Looks kind of very similar to this thing here, but we're quite a bit of ways away from 10 to the -6, so we don't have to worry about kW. So now I can pull out my calculator and do something like this. POH equals -log of this number. Alright, now that's POH. So now I'm going to use this PKW equals pH plus POH. That kind of reminds me of that log identity when I have KW equals, take the log both sides. There's that log of the sum is equal to the log of the, or the log of a product is equal to the log of the sum. Alright, so pH is going to be equal to 14 minus 4 equals 10. So here we go. Question mark. Answer, pH of 10. So now my question is, what was the change in pH? We went from 4 to 6. That's like a change in pH of 6. Alright, so the point of all this discussion was to make sure you could just calculate the pH of diluting strong acids and bases. And that's all we did here when we added a small amount to some pure water. Notice when you rearrange this for M2, when you rearrange it for M2, you get something that looks like this. Here's a dilution factor. Here's our first molarity. Here's the dilution factor, 0.001 divided. So here's our V1 divided by V2. Here's our M1, gave us our M2. Same thing going on down here. Once I finally got down here, we had to do our stoichiometry first. Here's how many moles of hydroxide that was left. It all makes sense, right? You understand this general process. So, pure water is not a buffer. What do you have to have a buffer? That I told you like 10 minutes ago.
A weak acid and its conjugate base.
Right, a weak acid and its conjugate base.
Do they have to be on the same side?
Of the chemical arrow? It's in the same beaker. Think of it as we can approach equilibrium from either side. I'm gonna start here with my favorite word, imagine. So sodium hypochlorite, and how about 0.081 molar hypochlorous acid. So what's the neat thing about this pair? Let me give you a hint, they differ by 1 proton.
Conjugate bases.
So they're conjugate acid-base pairs. They differ by 1 proton. All right, and then we'll ask the question. What is this solution's pH? Now we probably need something I haven't given anybody yet. So we have a Ka for this acid. Let me just put this acid in here. And the Ka of this thing, 3 times 10 to the 8, we say its pKa is 7.53. So students don't like buffers. I cannot understand why. We don't need an ice table. It's real nice. I'm going to use this equation here. And I'm going to go pH is equal to 7.53 plus the log of, and I have these concentrations. My anion is 0.024 molar, and the acid is 0.081 molar. And then sometimes I like to say, what's molarity divided by molarity?
Not molarity.
Or if I go moles per liter divided by moles per liter. So the nice thing about this ratio is that it can be unitless. So that makes life a little simpler, that it's unitless. I just need to know the mole ratio. I don't need to actually know the exact molarity. But one molarity ratio to another molarity is going to have a mole ratio that's the same ratio. So now I pull out my calculator and I go 7.53 plus the log. Of course, I want to be sure that I do this division and then take the log of that. And that's about the same pH as our artesian spring water we just had earlier. So what do you suppose I want to do to this water?
Hydrochloric acid.
Add
Something.
hydrochloric acid, right? You're reading my mind. We're going to add 1 ml. And to compare this to pure water, we're going to add the exact same amount of the same stuff, HCl. So before we get too far along, we need to find the moles of weak acid that we have. And so I'm going to take my molarity of the weak acid. Maybe I'll go ahead and write down what that is. I kind of got sloppy. I was so excited with there. And uppercase M, it's not looking very uppercase. And it says I have 1 liter, right? Well, that's convenient. That means I have that many moles of hypochlorous acid. And while we're here, let's go moles of conjugate base. So I'm going to take that molarity. There's our conjugate base. Molarity times volume equals moles, because molarity is moles per liter. I'm going to run out of whiteboard real estate in a second.
Did we answer the second question?
This question here?
What is the pH after adding?
No, we're working on it. We're setting everything up. Well, we found the pH of the buffer system, where we have a buffer, so much sodium hypochlorite and so much hypochlorous acid, and we used the Henderson Hasselbalch equation to do that. All right, so now we're doing our mole accounting. We figured out how many moles of the weak acid we have. We figured out how many moles of its conjugate base. So what happens when protons is added to the system? And that's what we have. We have a buffer system. Here's what I've written down. Here's a proton. Here's some conjugate base. Now this is strong acid. We say strong acid reacts completely with a weak base. So this is what happens. We take some of our conjugate base and we turn it into weak acid. So then that allows me to somewhere figure out I have 0.1 molar HCl and I add 0.001 liters. That equals 0.0001 moles, right? So if I wrote down my moles here, I have it here, but adding a certain amount of moles of this is going to deplete that and add some of this. So I should have just left myself a little more space there. My moles of this is going to increase by that amount. And this thing here is going to go away by that amount. All right, so here I'm going to have 0.0811 moles of my weak acid. And over here I'm going to write it down here. I'm running out of room. 0.239. So now we're ready to go. I get to plug this back into my Henderson Hasselbalch equation. Since I'm running out of real estate, I'm going to just plug in these new values, punch that into my calculator, and here's what I get. So we've answered the question. pH now equals 6.99. What type of change of pH is that?
0.0.
Well, I subtracted these numbers and I got 0.003. I'll go with that. So quickly, we're going to just add 2 mils of base. as before. 2 mils, 0.1 molar hydroxide. So hydroxide converts weak acid to conjugate base. So quickly, I'm gonna go like this and say, how many moles is this? I think it's something like 0.0002 moles. And then I can probably take my old amounts here, 811 moles of HClO, and I'm going to subtract 0.0002, and I'm going to do the same thing here with 0.0239, and I'm going to add 0.0002, and I'm going to get 0.0209 moles of our weak acid, and over here I'm going to get 0.0241 moles of our conjugate base. So let's plug in these two new numbers. I plug those in there. I'm going to get a pH that looks like this. Now let's just think about the water. Our water, we started out at a pH of 7, and then we added some HCl, and we dropped down to a pH of 4. Then we added some hydroxide, and we shot up to a pH of 10. Now, to this buffer system, I added the same amount of strong acid and strong base. And look how the buffer resisted a change in pH. How did it do that? Well, adding strong acid or strong base changed this ratio. You know, and we had a whole liter with these molar concentrations, and we see it didn't change a whole lot, and it tried to hold the pH close to that. And of course, I figured out the magical ratio to get this close to 7. So behold the power of a buffer. And you create a buffer whenever you titrate a weak acid with a strong base. That's what we'll talk about Wednesday.